Okay, welcome everybody. How's it going? It's a historic day, I guess. I don't know if we'll know the history though by the end of the day. I'm guessing not, but it is a historic day. I'd just like to bring this syllabus up, if I can. Oops, maybe I can't. Let me see if I've got the skills. Okay, maybe I don't. Maybe I do. All right. Okay, so if you look at the syllabus, which is hard to see here, Exam 2 is on Tuesday, the 19th of November. So that means that we will be responsible through session 19 for the exam. Does that make sense? So we're not the exam will not get to absolute maximum shear stress, which is kind of a nice culminating result from all this time doing plane stress, but it won't be on the exam. And this homework will be due after the exam, right? So this homework is due, the one on session 20, that will be due on 11/22. Okay, any questions on the logistics? We'll send out new but informed seating assignments for where to take the exam. If you have, for some reason, a preference, say, hey, that really didn't work out last time where you assigned me, let us know before we post the seating assignments, okay? Okay, good, all right, that's that. Are there any kind of quickish or not quickish questions about combined loading that you would like to cover just off the fly, on the fly? We were just talking up here a little bit, and I think there's kind of this a little bit of discomfort in terms of which stresses you can add to each other and which stresses you cannot add to each other. Okay, so for example, if I have a beam, whoops, let's see if this works. And yep. Oh, wow, maybe. There we go. I don't know why it didn't work a second ago. Okay, so we have a beam that is being pulled by some force P. Okay, it's really a bar. Okay, and so what is, if I give you the cross-sectional area here, right? What is, and if I say this is the x direction, what is your choice? What would you put down for the state of stress in this beam or this bar? Anywhere? Anyone? Yes?
The normal stress P over A.
Yeah, right. So we have everywhere P over A. That's it. Okay? So the bars are the simple ones, right, with the axial loading. Now, if we came along, right, and we said, here is a bar, but now I've got some MAP applied to it, okay, on either side. Is the stress uniform throughout this bar? No, it's not, right? Is it uniform, though, at a given distance away from the neutral axis? So, right, if I've got my distance from the neutral axis, is the stress at along the length? So if I have an x equals, 0.1 L, and I have x equals 0.9 L, and y is equal to whatever, but it's the same. Is that stress going to be the same? Yeah, it is, right? Because why? Because for this particular beam, if I draw the bending stress diagram, it's just a constant, right? It's just MAP. Okay, so that means that the bending moment is constant across it. Now, if we said that we now added an axial load, P, to this system, what would you say, how would you go about describing the state of stress at a given location? Let's say that, I don't know, y is equal to 0.1 times the thickness, h, of the beam. And I say at any x, what is the state of stress? What are you going to do? I'll go ahead and I say, all right, we know it's a rectangular beam. It has a width b. It has some height h. Okay. What is the how? Go ahead, start spewing some algebra. Yes, Mark.
It has a stress from the p-value and the bending stress.
Okay. Yeah. So we're going to say, the sigma total, and are there any? So in this case, right? Are there any shear stresses involved? First off, so I'm making an assumption that there's only normal stresses. Yeah, but are there any shear stresses involved here? What? Why do you say that, Stephen? Okay, this is a very interesting point. Are you right? Who agrees with Stephen? Is there a shear stress present in this beam? Yes, you agree. Okay, all right. What is the equation for shear stress? VQ over IT. Okay? Also, what is the relationship between moment and shear force? Right? dm dx is equal to V. Well, what is dm dx here? Okay, so so m is constant. What is dm dx? 0, right? So this is going to be equal to 0. So this is a scenario where there's actually no shear stress. Okay, there's just bending, there's a constant bending moment across the beam. All right, this is one of the reasons why you're starting to see more of these, I'm just applying a moment, right? Because we're trying to keep it simple. If I apply a transverse force, then I have a change in the bending moment. Then it's dependent on, the bending moment is going to be dependent on where I am along the beam in many cases. Okay, and then I'm going to also have a shear stress. All right, or I'm going to have a shear force internally, and I'm going to have a transverse shear stress. Okay, so this is a case where the sigma total, right? You could write it as it's going to be, let's just call it a sigma p plus a sigma m app, and these, of course, are going to be in the x directions. All right, the way we've been drawing things here. Okay, so if now y is above the neutral axis, is MAP contributing a compressive or tensile stress? Oh, you were scratching your head? Someone else. Mark and Stephen, I know you know what's going on here, but someone else. If y is above the neutral axis, which I said y equals 0.1h, and I defined it that way, right? So is the bending stress from MAT going to be positive or negative? Yes.
Negative.
Negative, right? And how did you come to that conclusion?
Well, since MAT is shown there as counterclockwise.
Yeah. At least on one side it is.
The neutral, since it's of the neutral axis, it's be positive.
Yeah. So this is where we use the think method, right? We look at it and we say, hey, if I just make it smile, I can't do it very well. I can smile, all right, but I mean, you know what I'm getting at. So if I put a moment on it like this, right? It's natural that we expect that this thing's going to bow a little bit downward. I don't want to break this nice little pen here, but it's going to put the top in compression and the bottom in tension, right? The contribution from P, right, as long as P is positive and it's in the direction shown, P is going to be giving a positive stress across the board, right? So there are a couple ways we can write this out, but in kind of quickly, right, we're going to have a P over A plus, and I'll go ahead and use plus here, right? And then I'll say negative my over I, right? And I, well, A is equal to BH, and I is equal to BH cubed over 12, right? And so that describes the state of stress pretty much anywhere, right? Y is now, I didn't even specify what Y is, but that's the state of stress along that entire structure. Okay? Normal stresses are probably the easier ones to handle. Okay? Again, this is just on the fly, so if I make a mistake, please forgive me. But let's go ahead and let's talk a little bit about cases where you can have combined shear stresses. Okay? So for those, let's see if I can change the color of the pen. Actually, I'm going to use, this is like what I don't like when someone makes a mess and they expect me just to follow along, but I'm going to do it. All right? Here, let's consider our humble cylindrical beam that is also a rod. Okay? And let's say that this is X coming out like that. And for the sake of simplicity, let's apply a torque like this. We'll call that tap, T-ap, all right? And you see that what I did, I didn't have to do that, but I went ahead and I chose to make it follow the right-hand rule for the X, okay? Because it's an externally applied load, right? The load could be whatever you want it to be when it's externally applied. Okay? And then let's go ahead and let's look at what happens when we apply a P at the end. Okay? So this P is going to be causing there to be both a bending stress, okay, and it will also be causing a transverse shear stress. Okay, let's skip. We're going to skip. So we're going to ignore for now. We're just going to ignore the bending stress. Okay, it's not that complicated. Okay, because it's just going to be a function of x. Okay, well it's the quantity p times quantity L minus x. All right, but I don't want to do it. I don't want to do it right now. Okay, but that would be negative m. I guess I am doing it, but it's negative my over I, where I have that m being equal to the quantity p times quantity L minus x. All right, but we're not doing that. Or actually, it's actually p times quantity x minus L, right? Because it's negative. Nope, it's positive because of the way it's drawn. So that's why I didn't want to do it. Okay, so let's just talk about the shear stresses here. So one thing to note, and I think it's maybe more difficult to the transverse shear stress, so let's talk about that one first. The transverse shear stress is caused from the P. Okay? And if I took a slice along the beam, okay, what, not stresses now, not stresses, but if I took a slice there, what would the internal shear force look like? Yes?
Just negative P.
Okay. Actually, no, it's just positive P. Okay? It's going to be exactly like it's drawn here.
Oh, because of the reaction.
Yeah, exactly. See, you just got it, right? And this is one of the things I tried to explain in the video, right? So if you go back to the, I think, question 3 video from last night or yesterday, okay, what you'll see is I went through the whole exercise of, look, here's what the beam looks like, this is the reaction force, then therefore, when you take the slice, you just gotta know at this point that with the conventions we're using, at least, that the internal shear force on this slice is going to be in the same direction and at the same magnitude as whatever's applied at the end of the cantilever. Okay? So that's what the internal shear force looks like. And we could go through the exercise, right, where tau is equal to VQ over IT, right? That's perfectly fair game. And that would be necessary to figure out where we are. So like if I'm like in the middle, like I'm not at the center, but I'm not at the top, right? If I'm in the middle, then yeah, I gotta do VQ over IT. All right? That's just what I have to do. Okay? But normally I don't ask that question. All right. So okay, but let's go ahead and say, okay, let's just say we are interested in those shear stresses. So we have a bunch of shear stresses. Okay. Oops, okay, it doesn't let me do that. Okay, we have a bunch of shear stresses, right? They're all like all over the place. They're smaller up here. Okay, that's really bad. I wish I was doing this I should have probably just done this on a new sheet. But these stresses, okay, on that face, right? What would be the subscript that I would use for that tau? Well, you need to know some other information, right? Because I have only defined x. Okay, so let's say that we do y in that direction, and let's do z in that direction, upward. Okay, that's a right-handed coordinate system. Also, call me if I ever use a non-right-handed, a left-handed coordinate system, right? But x cross y gives us z. Okay, so if we're thinking about what the state of stress is on that face, on this face, what would the subscripts that I use for the stress now? Yes, Mark.
Tau.
Yeah, tau xz. Why?
X you see in space, and then it's in the shear is in the z direction.
Right. Okay. So does everyone see that? This is an x face, right, with shear force in plus z. Okay, so that means that it's got to be tau xz. Okay. And so, if I want to be general, I could say, oh, it's VQ over IT. Okay. If this is the tau xz due to P. Now, let's go ahead and let's pick a spot. The spot we're going to pick will be on the side here. Okay, let's call this point A. All right, and so if you're thinking about it, it's kind of like on the neutral axis, at least a horizontal neutral axis, in the y direction. Okay. So, and it's the most positive y. It's on the outer edge. Okay, so it's out there, right? So if I'm looking at tau xz at A due to P. All right. Yes, that's pretty bad. That's tricky, right? What would you write there? And I'll go further and I'll say, okay, there's a radius lowercase c. What would I write there? Just due to P at this point. It's on the neutral axis. Someone? Come on. Someone else. Someone else. This was essentially on the homework last night. Huh? So just yeah, what's that? Okay, so I agree that it has, we'll call it P over pi c squared, okay, just because A was reserved as a point. But I need a coefficient, right? Right? What's the coefficient? Yes. 4/3, okay? So if you look in the notes when we were covering the transverse shear stress, we said, hey, if it's a circular cross section, the maximum transverse shear stress due to in a beam, all right, it's going to be 4/3 times the average shear stress. Okay. If it's a rectangular cross section, then it's 3/2 times the average shear stress. And so we derive that. So you don't derive that every time, okay? Because there's a very good chance I'm just going to say, or I'm going to make it such that it's on the neutral axis, and so you're looking at the maximum transverse shear stress. Okay. Now, that's just for the P. What's happening with the T-app? What's happening with T-app? So I've already selected a spot. Okay, it's this the spot I selected, right, is A, right, and that's on the y-axis, and I've got this T-app being applied. So what is the, before we even kind of figure out a quantitative answer, what does the stress from T-app look like at A? Like, just qualitatively, use the think method. What's happening there? Yes, Stephen?
Stress is moving upwards.
Yes, right, exactly, right? So if we look at this cross section, okay, and here is A, okay, what you have is that there's going to be a shear stress like that, and as we get closer, as rho gets closer to 0, right, it goes down. So there's a shear stress that is going to be maximizing, or it's a maximum at A, where rho equals C. What is that quantity? Now I want the actual quantity. Yeah, I heard it, right? TC and J, right? So it's going to be the T-app times C over J, all right? And what is the subscript for my shear stress? Someone else. What's the subscript for the shear stress? I see you pointing. What are you pointing at? It's up. Okay, so that would be, and what's up in this problem? It's a z direction, right? Okay, and on which face is it acting? X, right? So that's going to be tau subscript xz, right? Okay, good. And this is at A due to T-app. Okay? Any questions on this? Yes, Brennan.
So this might be a silly question, but doesn't the tap, could that move A off in neutral axis?
Very, very small amount. Very, very small amount, right? So we're assuming small deformations, and so for our intents and purposes, it's on the neutral axis. Okay. Good. Okay. So I guess if you were to say what is the shear stress here, what would you say? You would say it's going to be 4/3 P over pi c squared plus this Tap C over J, right? And that would describe the shear stress. If we want the normal stress, then we have to go about doing the negative my over I, okay? Which we said we're not going to talk about it right now. Any questions or thoughts on this? Insights you would like to share? Have you come up with any tricks to be able to do these types of problems yet? I think it's helpful to be able to think about the deformation, right? So, like, if you have to take your eraser on your pencil and twist it, right, and push it and pull it during the exam, I'm not going to fault you for that, okay? Because that deformation is going to help us understand what's happening with the direction, whether it's positive, whether it's minus, okay, and whether and what's happening with the twisting. Okay. All right, that was a long detour away from what I wanted to talk about. These are very important concepts with combined loading because it's going to make most of what we cover from here on, if we don't have this straightened out, it's going to make it very difficult. Okay. Today, not so much. All right. Today we're going to talk about something else that's kind of tricky. Okay. But once we start doing problems that have structures in them, you're going to use what we do today. Well, actually, I'm probably not going to use what we do exactly today, but you're going to use the concepts that we talk about today through more circle in the future. Okay. With the combined loading. Right? The idea here, what's the big deal? The deal here is that we are trying to be able to say, here is a structure. You apply loads to it. Figure out what the state of stress is at the most critical part that you think might break. And make sure that that is not going to break there. Okay? That's what we're trying to do. Right, we're trying to figure out how to describe the state of stress essentially throughout an entire object. And even if you're looking at the finite element analysis, right? You're like, ooh, nice, pretty color pictures, right? We want to be able to understand what those pretty color pictures mean, and it's not just it's not just, oh, the color is less than this value. Actually, we do some dumb things, some very smart things to kind of make it that way later in the class, okay? That you use something called the von Mises, or you could calculate an equivalent stress so that you can do that, all right? But the point is we want to be able to understand how to describe these 2.5D types of systems and their stresses that they might have, okay? So let's go on. Today, we're going to use method of sections again. And this time, we're going to use it with rotated elements. We're going to transform material elements. And so you're going to see lots of these pictures, but imagine that you have the state of orange stress. Right? So you did your combined loading analysis, right? You just saw that when we had this beam, it had some tau, I need this. It had some tau xy, it had some sigma x, right? And now we're saying we're going to rotate that element. We're going to look at it from a different perspective, and there are going to be a new set of stresses. Now, the state of stress, these are equivalent states of stress, okay? But by rotating, sometimes we get a simpler description that allows us to relate more closely to the material testing that we might have done. Okay, you're like, wait, why? Isn't it just nice that, no, we want to be able to rotate the element to be able to get to a more relatable depiction of the stresses. Okay, I hope that will become more clear. And we're going to use this. I don't expect you to understand right now, but I do expect you to understand this in about 15 minutes. Okay? And this is one of the ways that we perform this equilibrium to figure out these equivalent stresses. We're going to then completely skip this technique and say, here are the generalized equations for these 2D transformations. Okay? So you'll write these equations on your sheet, and then I will ask you on the exam to do it the old-fashioned way, and you will check without telling me that it matches with your 2D transformations or your equations, okay? You got that? And if you do not do it the old-fashioned way, if you bypass it and do this way, you will not get full credit. And you can take a look at the previous exams to see examples of this being asked. And then we'll talk a little bit about stress tensors and rotations and how you can do this in Python or how you can use linear algebra to perform these calculations. And that is not that exciting, or that, what is that? For you, it's not that exciting because I wouldn't ask you to use stress tensors on an exam. So you're like, oh, okay, shut that off. I don't really need that. But there's a question that kind of gets to this point, and I think it's good to know. So if you take a grad class or you do further work in mechanics, you'll be able to understand how these tensors are relatable to each other. So let's go to a generalized depiction of stress. We have 6 terms. At this point, we're familiar with sigma x, sigma y, sigma z, sigma xz, or it could be sigma xz, but usually tau xz, tau xy, and tau yz. So those are 6. And those 6 terms, 3 normal stresses, okay, not principal yet, 3 normal stresses and 3 shear stresses allow us to describe the state of stress in 3D, okay, for a linear isotropic material. The tensor, right, is going to be a collection of numbers that maintain their meaning under transformation. So you can watch this fun YouTube video on what the heck is a tensor. It's illuminating. The basic idea, though, is that if you rotate the material element, well, okay, so for us, since we're doing mechanics, so we rotate the material element, we get a new a new depiction of equivalent stresses, and that's going to be equivalent to the original state of depicted stresses. And so that's what we do. That's how we connect the tensor math to a physical system. But you know, if you're just like going, hey, I want to just look at the math, the tensor says that if you rotate it, or if the property of a tensor is that if we rotate it, it's going to give us an equivalent depiction of what's happening. So let's just refresh our memories in terms of how to draw these stresses, and we've already been doing this. We've got a sigma x on one side. We've got maybe a tau xy. We've got maybe a tau xz. We've got other stresses on another face that we can draw out. That's a sigma y coming out there. We have a tau yx. We have a tau yz. And we've got this face here, right? And so when you think about it, a tensor is not a bad way to depict all this information, because there's quite a bit happening on the face of a material element. But again, we only need 2 subscripts, right? Don't go into another class and say, oh yeah, but we discussed tensors. Aaron said that we just needed 3 subscripts. Be like, what? No, 2 subscripts, 3 values for each of those subscripts. Okay, for at least for 3D. Okay, And we discussed before, like if it's in the minus y direction on the minus y face, then that's going to be equivalent to sigma y. And then if you look online, you'll see some kinds of fun depictions of stresses on faces. And you know, one thing that, how do you say it? We may have forgotten, right? Is that in reality, these stresses that we're talking about are representing components of a traction vector, okay? That is kind of this internal force or internal load that you might have in your element, in your material, in your structure. Okay? These stresses allow us, these are the components, right? Because these stresses are in fact scalars. The Cauchy stress tensor can be written like this. We typically write it like this. Okay? It's the same thing though. Okay? 1 for x, or x for 1, 2 for y, y for 2, 3 for z, z for 3. All right? And so we be. Okay, now we're going to talk about a particular type, right? If you look back to the title of these slides, you're like, it said plane stress. You haven't even told us what plane stress is. Okay, well, here we go. Plane stress typically is going to be on a thin sheet of material. And plane stress, yes, as you can imagine, it means plane in the sense of planar, right? Not in the sense of vanilla yogurt. Actually, vanilla yogurt is not plain yogurt, right? That's right. Yeah, plain yogurt is plain yogurt. Okay, never mind. Okay, so here the normal stress perpendicular to the plate or the plane is going to be equal to 0. You can still have shear stresses in the plane, but again, the shear stresses out of the plane are going to be equal to 0. So think back to the thin-walled pressure vessel. What do you see there? Remember, we said I've got a sigma 1, I've got a sigma 2, and I don't have a sigma 3. Right? We said that sigma 3 was going to be really small. All right, so we have sigma 1, we have sigma 2, okay, and the sigma 3, we said it's going to be, Professor Roylance was talking about, okay, there's not an appreciable thickness for it to, or it's diminished. I don't remember what the exact fancy words to use, right? But there's not appreciable thickness, essentially, for us to build up stress in the z direction, okay? In the radial direction if it's a pressure vessel. Or the way I look at it more simplistically is that there's a pressure on the inside, there's no pressure on the outside, and the pressure and the stresses in plane are a lot larger than the pressure that we're applying to that system. Okay, so sigma 1 and sigma 2 are going to be much, much greater than the pressure, or whatever we would consider to be sigma 3, right? Because the R divided by T, the radius divided by the thickness for these thin-walled pressure vessels is a factor of 10 or more. So this is kind of a real-world example. The thin-walled pressure vessel is a real-world example of plane stress. Now, what does this mean if you had a 3D element of stress, or a 3D depiction, right? So here, X, Y, Z, here's the cube. Here are going to be our stresses. We have, let's say, a sigma X. We have another sigma X on the other side. We have a sigma Y. We have another sigma Y on the other side. We have our shear stress, tau xy. We have another shear stress that matches that one. And then we have two more that allow us to stay in equilibrium. All right, you see that? That is in a state of plane stress. What are we missing? We're missing sigma y, we're missing sigma z, we're missing tau yz, and we're missing tau xz. Okay. We only have sigma x, sigma y, and tau xy. Is this? I see some alertness, some smiles, and Well, yes, but is there any thoughts or questions on this so far? Okay. Yeah. All right, it is what it is. So the 2D representation for plane stress is surprise, surprise, surprise. You've never seen one of these before. It's just a box with sigma x and sigma y and tau xy. And remember, I talked about this a little bit in one of the questions, right? If I know tau, if I know one face of the shear stress, I know all four faces, right? You just got to get one of them right. All right, so here, you can think about how to do it. Not always, but I think of the the arrows have to be pointing to each other. Okay, they have to be pointing to each other. So, I'm going to put one up here to be pointing to it. But you can do it a different way if you want. You can say, this is up. All right, so therefore I've got to have something down. Well, down to this side, I'm going to have down. All right, because I don't want it to move vertically. But then that causes counterclockwise rotation. So then I got to have something on maybe this side that's going this direction, okay, to compensate for that. So here we have these arrows that we draw as such. Okay. This is the standard. All right. XY, this is the positive X face, this is the negative X face, this is the positive Y face, this is the negative Y face. This is how we do it. Who sings that? It's Saturday night, right? This is how we do it. This is how we do it. No? Is that from like the 90s? Okay. This is how we do it. Okay. All right, so now, when we have a transformation, what we're saying again is that we are going to define a stress at a point, okay, and these stresses on opposite sides of the cube, okay, are going to be equal and opposite to each other in magnitude. Okay, so that's fine. So we say, okay, now we put a dot in the middle. Woohoo! All right. Okay, so sorry. We're now going to do the transformation. This is how okay. This depiction of the stress is supposed to represent a location on your structure, right? So that makes sense, right? We've done finite element analysis. You know there's a stress distribution. We've done beams. We've done rods. We've done bars. We've done trusses. We've done thin wall pressure vessels, right? What else am I forgetting? We've done a bunch of different things, and so what we're saying is that every geometric location has a state of stress on it. And we put that little dot in the middle, which I often forget to put, okay, but that describes where this element is on the structure. And of course, this is infinitely small. So when we apply a rotation, we go from this is just exactly the same drawing, to something like this. So for our intents and purposes, we're only rotating about this point, and we're only rotating about an axis that is normal to the page. Okay. So here you see we've rotated by some theta. Okay, so this x was, and one way to look at it is this x, right? Sigma x, this x was there, and now this x prime, okay, is at some angle relative to the original x. You see this? So we're going to say that theta is the amount we rotate. And there are other ways to look at that data. You could look at it down here if you want. Okay? And so this is just to give us an idea, okay, of what a transformation looks like qualitatively. Okay? We haven't figured out how to quantify these new stresses. This is just what we're doing. Okay? And you can think of going back to what's happening here is if I took a slice. So here is a slice that greenish, nice, grassy looking color in there. I guess my grass doesn't look like that. My grass is kind of brown. But you see, like that's a plane there, right? And what I'm saying is, at a particular location, essentially this could be a different plane that I've put in, and now I'm looking at a new state of equivalent stresses. Okay. Yeah, I didn't say it, but we usually say, okay, sigma x becomes sigma x prime, tau xy becomes tau x prime y prime, or tau prime xy, whatever, and then sigma y becomes sigma y prime. Okay, so we're dealing with, this is essentially, this is the x prime direction, this is the y prime direction. For your other classes, have you had to do rotations before? I mean, of course, we've all looked at how a wheel rotates. Okay. But have any of your classes required to do transformations, rotations? Okay, well, this is your first time. Woohoo! Okay. How are we going to get from our sigma x, sigma y, tau xy to sigma x prime, sigma y prime, and tau x prime, y prime? Okay. We have three. This is plane stress. We have three stresses. We need to get three new stresses. So here is one approach. We start with the element having known stresses. We rotate it by theta. Then we use method of sections. We take a cut, right? And we do equilibrium. And then we might also take another cut. So we can repeat for y prime. Okay? And this is the process. So it sounds very simple. In practice, it's a little bit tricky. Okay? And it's a little bit of a mind bender. So here we go. We take this element that has the state of stress that we love, and we rotate it by some amount, theta, and we then say, okay, it's got a sigma x prime, tau x prime, y prime, and it has also sigma y prime, and we can draw the rest of the arrows on it. Okay, so it's like, okay, you just repeated exactly what we did before. Okay, and again, this is the question. How do we relate the sigma x, the sigma y, the tau x y to the sigma x prime, the sigma y prime, and the tau x prime y prime? And this is how we do it. Where is my laser pointer? Okay, all right, what have I drawn here? This right angle corresponds to this right angle right there. Okay? And then this point is this point here. Okay? So we've drawn just from this top left down partially to that location. Okay? And then we slice. Right? So this represents a slice from here to here of the original element. The x direction is still what we had before. Okay, that was still horizontal. The y direction is still what we had before. That's vertical. The x prime direction, though, is orthogonal to this slice. Okay, you see that? This purple is normal or perpendicular to this purple. And it's off from x at some given angle. Y prime is in line with the slice. Okay. And this is an interesting thing. We have now a hypotenuse here. Okay. And we call that hypotenuse delta A. You're like, wait, but it's a line. Okay, so this is where we say stresses have to be what? Some unit of force divided by area. Okay. So even though this is a plane element, what we're actually doing is we're saying this has some length, okay, the hypotenuse, but this whole element is actually going into the board or into the screen or into your piece of paper by some depth. Okay, we don't actually typically give it a letter, okay, but it's some depth. So this hypotenuse is really some area that's related to the hypotenuse and the depth into the board. Okay, does that make sense? So like, you know, I could say, oh, there was some area over here, all right, associated with this face. There was some area on the bottom face, all right, and now I've introduced some area here that's on the slice. So A, and now this is the delta A. That's the hypotenuse. This is where things get kind of funny. Look at this. We're going to say this remaining area here. All right, this is the hypotenuse. Now, this is another thing, another tip. When you're drawing these diagrams, it's nice if someone says the angle of rotation is 45 degrees, which is very common. 45 degrees is an important angle of rotation in mechanics. Okay? But don't draw it with 45 degrees. Do you see that I have a small angle here, and I have a larger angle here? Okay? That's on purpose. I am trying to make sure that I keep track of this small angle, and I know where it is because this small angle is equal to this small angle. Do you see that? All right. And you can do whatever the alternate interior, the AIA and the, I don't know, all the acronyms they have for figuring out the different, geometry. I can't remember. Like, I don't know. Did any of you, actually, did you do the new math? Did you grow up with the new math? Because the new math is very interesting, but my kids, they tell me, like, I gotta do this, and I'm like, I don't have a clue what terms you're using to calculate these things. I mean, I can do that. I can tell you how to do it, but no, we use these like line graphs and these other things. And I'm like, what? I don't know. So anyway, it's fun. It's fun. And they're like, no, Dad, you're not very smart. And I'm like, well, actually, intelligence is not dependent. Actually, they don't call me not very smart. They're kinder than that. But that's like the look I get, right? It's like, just because I don't know your terminology doesn't mean I'm an idiot, okay? There's some profundity to that, maybe. All right, so anyway, this side is delta A sine theta, so this side is going to be delta A cosine theta. Okay, everyone see that? It's because it's based on this small angle, which is the same as this angle, theta, for the rotation, not this angle. Okay? So now we can go a little bit further, and we can say that this force acting on this purple face associated with a normal stress is going to be sigma x prime delta A. Does everyone see that? I know we're going at a pace, I hope that this makes sense. Remember, I've said this I think multiple times. When we do equilibrium, it's not equilibrium of stresses. Yes, we just did combined loading and we added stresses to each other. So you're like, that is, no it isn't. Okay? We have to think about forces and moments. Right? And so here, what we're beginning to say is this is a static structure. It's a static structure and it has to be under equilibrium. Okay? I took a slice, right? It was under equilibrium before I took the slice, right? It was a static structure and then I took a slice and now I'm doing the same thing we've done in other structures. That still has to be under equilibrium after I've taken the slice. So I want to be able to come up with a set of forces. We're actually not going to use equilibrium of moments. I know it's sad. Are you sad? Maybe you're a little bit sad. But we're going to use equilibrium of forces, okay, to be able to figure out what these new stresses are. Remember that we have a sigma y acting on this face. Yes, the face is a little bit less than it was before, but that stress is constant along that face. And it's acting on that area, delta A sine theta. So we have a sigma y, delta A sine theta. And we can also say, hey, there was a shear stress on that bottom face. Again, it's a shorter face than what we had up here, but it's tau xy acting over delta A sine theta. You see where this is going? And we can do the same thing on this face. Okay. Does everyone see where we got these? We didn't do anything rocket science-y. We're using method of sections yet again. And what we're saying is this element up here was in equilibrium before I sliced it. I slice it. This slice still has to be in equilibrium. And now I sliced it so that I have two faces that are part of the original left, or the left and bottom of that face. But now I've got a new slice that corresponds to the face over here of this rotated element. So now that I've drawn all these stresses out, how would you do equilibrium here? What would your approach be? I will talk about one other thing before we get to this, but yeah, Stephen, what were you going to say? Yeah.
Since you have the stress in the an area, right? Couldn't you use that to calculate the force?
Yeah, exactly, right? We're going to come up with a bunch of equivalent forces, and we're going to perform equilibrium, right, in appropriate directions, in two orthogonal directions. Okay? Yes?
Just to clarify, delta A is the length.
Delta A is a length, and delta A is the hypotenuse of this triangle, but so the delta A's are all going to cancel out, but it's really supposed to be an area, right? It's a length times the depth into the board, right? So imagine, right, because I can't have a force acting on a line. I mean, you can have kind of like distributed forces, right? But this is because I'm dealing with forces, I'm saying that this actually has 3D nature to it. It's a stress acting on a face, on an area. Okay, so, but they're all the same, right? They're all the same depth, right? So, like this delta A, right? It's maybe, let's say it goes down depth B. This delta A sine theta, right? It's got this length and it goes down the same depth B. Into the board, into the plane. Okay. So yes, we're going to do equilibrium, just a second. But before we do that, I just want to also point out that you can slice a different way. you can make the purple correspond to the top of the rotated element. Why is this important? Well, look, this is the y prime direction, but notice, sigma y prime, nowhere to be found. Nowhere to be found here on this one. So we need sigma y prime, right? Sigma x prime is found here, tau x prime y prime is found here, but there's no sigma y prime. So this slice, this direction, this allows us to put a sigma y prime times delta A, this delta A now, for this hypotenuse, and be able to perform equilibrium on this sliced triangle. Okay. Does that make sense? Right? Now there's no sigma x prime here, right? Only sigma y prime and tau x prime y prime. So it turns out, if the question is asking you to figure out tau x prime y prime, you can choose either slice because you can solve for it in either one of these triangles. Okay? But if it's asking for a sigma x prime, at least the way we defined it here, then you're going to want to slice this way. If it asks for sigma y prime, you're going to need to slice it this way. If it asks for both, then you've got to do both. Okay? All right, but tau x prime y prime is more flexible here. You can get it from either of these. Okay, so let's do an example. Here, okay. So let's say that you have a sigma x equal 50 megapascals, a sigma y equals 100 megapascals, and a tau xy equals 0. Okay. Question is, what are sigma x prime, sigma y prime, and tau x prime y prime when the angle of counterclockwise rotation theta is 30 degrees. So isn't this nice? You know, we've done so many things that were just kind of algebraic. This is actually using numbers. Okay? And this is one case where, one type of problem where, you can use the, we will have a generalized description, but it's often not a bad idea to use numbers. Okay? So what do we have here? We have an element that we've rotated, amount theta. That's going to be 30 degrees. We have our sigma x prime. We're going to have our sigma y prime. We're going to have our tau x prime y prime as well. Okay. Okay. The suspense. All right. It's the suspense. Yes. Please use exaggerated angles, meaning whatever. Like make this a very small angle. Okay, even though it's 30 degrees, make it like 15, just so that you can keep track of where the small angle is. And here we go. So we have the 30 degrees in there. Okay, we have our y prime like this. All right, and we're going to slice like this. Okay, and we have our delta A there. We have our delta A sine 30 degrees. Our delta A cosine 30 degrees, and we have this 50 megapascals, and now something interesting. Okay, we are going to have an angle there as well. Okay, there will be another angle there. Okay, now what in the world happened here? Well, we need to equate the component of stress from sigma x, right, to this same direction, right? I can't say, hey, 50 delta A cosine 30 degrees, even though that's a face, is equal to sigma x prime times delta A. Cannot do that. Why not? Why can't I just add or subtract those vectors with each other? They're not in the same direction, right? They're not in the same direction. So what I have to do is an additional little tricky rule. Okay, we have to come up with a component of the stress that's in the same direction as x prime. Okay, so we are going to sum the forces in the x prime direction and in the y prime direction. Okay, and set them equal to 0. Right, that's what we use from equilibrium. So that was this is the new piece of information that I did not share on the previous slides. Was just trying to emphasize these areas. Okay, but now I got to also figure out what this direction in the same direction as x prime might be. Now, is this, say I have 50 here, is the magnitude of this vector that I'm whatever moving on, is that magnitude, is that going to be less or is it going to be greater than 50? Less. Why is it going to be less?
Multiply by cosine 30.
Okay, yeah, so you multiply by cosine 30, yeah. Yeah, so this is the hypotenuse, right? This is where things get, you had to keep track of your hypotenuse, what are they? Hypotenuses? Okay, so yeah, this is your hypotenuse, right? That's like the vector, and what we're doing is we're breaking it into two orthogonal components. And someone already said it. That means that this component is going to be 50 times cosine theta. And again, this is why it's good to use exaggerated angles, right? Because you see, this is the tight one here, right? And this is the larger one here. And it makes it much simpler to figure out, okay, is it cosine or sine? This component over here is still going to be important. This component, this component, that is going to be useful if I want to look at the y prime direction and calculate out tau x prime y prime. Do you see that? Okay, so we continue. Sigma x prime delta a. All right? And we're setting all these things equal to 0. So you see that one's pretty straightforward, right? Sigma x prime times delta a. That will be a force in the x prime direction. Good. That's because I want to sum the forces in the x prime direction. All right? Now, this 50, this storied 50, all right, megapascals, is going in the opposite direction. So it's going to be minus, okay? And I already know that the component of the vector is going to be, like we said, cosine 30 degrees. All right, so that is 50 megapascals times cosine 30 degrees. But this is a stress still, or this is units of force per area. We have to multiply by an area. Which area do we multiply by? It's acting on this face, so it's acting delta A cosine 30 degrees. Like that. Is this fun? Maybe for some. For many, I don't think this is that fun. Okay. But, okay, you kind of get into the swing of things. All right, so now, what else is acting in the x prime direction? Well, not tau x prime y prime, that's orthogonal, so I don't have to worry about that one. There's 0 component of tau x prime y prime acting in the x prime direction, sorry. But down here, this 100 megapascals does have a component of its triangle that is acting in the same direction as x prime. And it's also very important to draw the arrows. You see this? So this vector is the magnitude, is the hypotenuse, right? And if to get there, right, vector addition, you remember that? You have to choose a path. So I'm going to say I go along this, and then I go along this to get there. I use vector addition to get to that end point of the vector, the head. So what is the component of stress? How am I going to describe this magnitude of this vector here? Yes?
Isn't sigma y tan 30 times delta A sine 30?
Okay, whoa. Okay, so that's interesting. Okay, I have to think about that. Sigma y. Okay, so sigma y, all right. You said tan 30 times what?
Times delta A
Oh, yeah. Okay. So, okay. Not tan. Okay, that I can tell you, not tan. What is it instead? I want this component. This is the hypotenuse.
Oh, that's the hypotenuse?
That's the hypotenuse.
That's sine.
That's right, exactly. You got it. All right, so it's going to be just sine theta. All right? So that's, and what is theta? Theta is 30. So here it's going to be minus, because it's going opposite direction, x prime is going, times the sine of 30 degrees. And now it's times, like, you're saying, what's your name? Isabella. Okay, Isabella, like she was saying, like you're saying, Isabella, that it's delta A sine 30 degrees, like that. Okay. All right, and this is equal to 0. So when you solve this equation, you knock out all the delta A's. You see all the delta A's disappeared? All right, and then you solve it and you get that sigma x prime is equal to 62.5 megapascals. Okay. The summation of the forces in the y prime direction. All right. Remember, y prime is this direction, and tau x prime, y prime is acting in it, but sigma x prime is not. So this is going to allow us to solve for tau x prime, y prime. So tau x prime, y prime times delta A, that's this hypotenuse and the depth. And we've got components, right? So we've got a component that will also be in the y prime, positive y prime over here. And this one is going to be in the minus y prime direction over here. Everyone see these? So plus 50 megapascals times sine of 30 degrees will give us this component. The delta, it's acting on the delta A cosine 30 face. And then minus the cosine of this, so this is hypotenuse, cosine of this, times, this is the delta A sine 30 degree face. And that equals 0. You knock out all the delta A's, or now cancel all the delta A's, and you can solve for tau x prime 1. Okay. Any questions on this? Yes? Okay, so the hypotenuses are the original vectors that you were given. Okay, right? Because you were given that x is this. I am breaking it down just to figure out what the contribution of that vector is in whatever plane or whatever angled line that I need to. Okay, so the sigma x and the sigma y, those are going to be your hypotenuses. Again, I guess they're hypotenuses, not hypotenusi or whatever. Okay. Other questions? Good questions. So we had to figure out what is it, sine or cosine for the faces, and we had to figure out if it's sine or cosine for the direction of the vectors. And then we had to do equilibrium. And that's it. This is a very powerful technique, though, because it shows us we didn't do anything rocket science-y. Right? We were saying, hey, I want to find the equivalent state of stress, and I want to do it at a rotated angle. All I've got to do is equilibrium. You know, all we need is love. Maybe in this class, all we need is equilibrium. Okay. All right, but the love just went out the window because we got to do it for sigma y prime as well. All right, so you got to do this again. And I'm running out of time, so I'll try to be kind of fast here. All right, and you can go through this if you like in more detail. But here we now have this top face, okay, and that's the face that's going to be parallel to sigma x prime. And sigma y prime is going to be orthogonal to it, and tau x prime, y prime will be acting on that face. Okay. And we can, once again, do equilibrium on the y prime and the x prime direction. So if you do this all out, okay, you get something like this. And you can use Colab if you like to solve it, and sigma y prime comes out to be this. Okay. Any questions on this? it's pretty straightforward, right? It's not bad. It's a process that I would like us to be able to master and be able to use, and then toss it away because you're not going to use this process, okay? Because it's time consuming. It's not time consuming for a computer, right? But there are actually faster ways for us to calculate stresses, rotated elements. Okay. This one had so the previous one had no tau xy on it. This example, which you can look at the notes, has a tau xy on it, which makes things even more tedious. You see, here's a tau xy, here's a tau xy here, okay, and then that one has components also, right? Two vectors that are going to be in the x prime and the y prime direction, and so also requires appropriate care. Okay, so it gets even longer. All right. Okay. Now, so there'll be some questions. The generalized equations essentially are doing exactly what we did, but using algebraic symbols, variables, instead of actual sigma x, equals 15 megapascals. And so these equations, if you go through them all, which I won't do right now, allow you, these allow you to shortcut what we just did. Okay, do you see that? You simply put in your sigma x, your sigma y, and your tau xy, and the angle of rotation that you want, and boom, out pops sigma x prime. Okay. Please, at least one time though, for your sake, do it the long way. And remember how to do it, because when we ask you to do it out the long way, you've got to be able to do it the long way. Okay? And why are we being so particular about that? Because it shows how you can figure out the equivalent stresses just by using equilibrium. All right, so if you're stuck on a stranded island and you don't have these equations with you, you could go ahead and rederive them if you wanted to. Has anyone ever thought about what they would do on a stranded island? No? You haven't thought about that? I think I knew one person I would say, I would try to get to like maybe Newton's laws. Right? I mean, you think about like how to, right, going through this. Actually, I think they said they would go farther, right? But that would be one thing you could do. You could rederive the laws of mechanics. All right? All right. The last thing, okay, that I just want to emphasize is that you can then use these expressions to plot as a function of the angle of rotation what the new stresses are. Okay? And doing that shows you that they can be maximized and minimized. Why would that be useful? Well, maybe I want to know what the maximum equivalent stress might be in a particular direction to figure out if it's going to fail. Okay? I'll try to do a little bit of video work on the tensor stuff, so that's not so bad, and I appreciate your time and patience. Let's do the attendance. Is it not? Okay, there we go. Do I dare? I don't know. I have no idea. There, just do that. Enjoy the next couple of days. I'll see you on Friday. Thank you.